instead of doing all the problems over again, I've already got them written out, so I'm just going to explain what I did. This is the second supplemental problem for Chapter 28. Here's the diagram. This resistance represents the joule heating, and the power on the load is the current times the voltage across the load. It's not ohmic, so I used the loop rule just because it's not ohmic. And I got this expression here then, that the voltage across the load equals the total voltage minus, I guess, whatever voltage is across this wire, this transmission wire. The efficiency is the power across the load over the total power, which is a percentage, essentially. I didn't realize when I first attempted this problem, so we need that to be as close to 1 as possible. So that would be as close to 100%. The closer it gets to 1. So I got this expression, which is the power of the load, I times the voltage across the load, over the I squared R loss, the joule heating, plus the power across the load, which is the total power. And then just algebraic manipulation, nothing crazy. I ended up coming to V minus IR over V, factored out that V, and you get 1 minus IR over V for the efficiency. So obviously we want this term here to be as close to 0 as possible so that just 1 is left over. And this gets closer to 0 as V gets larger, approaches infinity. So that's the answer to that problem. Next problem, I drew out this little diagram of an Earth. You know, this is the equator. It's kind of a 3D graph here, north, south, east, west, down, and up. And they give us this information in the problem. This is an electron. It's a little bit above the surface right here, and it's going east at this velocity. The magnetic field is going north, so it's perpendicular. The electric field is going down. So since this is an electron, that means that the force is going to be going up. But we'll talk about that in a second. This is the information for the electron. They want to know the forces. So gravity is just mass times gravity. Mass of the electron times 9.8 comes to 8.93 times 10 to the negative 31st. It's going down because it's gravity. This is that electric force. It's just the charge times the electric field. So charge of an electron times electric field. And it equals this, 1.602 10 to the negative 17 newtons. It's going up, opposite the electric field, because it has a negative charge. It's an electron. And then for the magnetic field, it's going to be it's QV cross B, but since they're perpendicular, like we saw here, it can just be QVB. That's how the cross product works. So just plugging in those numbers, we come up with the 4.806 times 10 to the negative 17th. That's going to be going down because the electron moving this way is like a proton moving this way. So if we do the right-hand rule, the field is our fingers, velocity is the thumb, and the force is the palm, which is going down. So that's how I got that one. Here we go. And then for this problem here, it talked about how the wire was bent into a loop, and the normal of the wire, which was this, I just kind of drew a circle, and the normal is coming out of it. So the normal is obviously perpendicular to the plane of the loop, but they're saying that the magnetic field is uniform and it's in the same plane, basically. They're saying it's perpendicular to the normal, which means of the loop, which means that it's the same plane as the loop. So the book gives this where the torque equals current times area times magnetic field. We can use this one. They give us a length of the wire, and they give us the magnetic field, and they give us the current. So just using geometry, we can find the length of each side. We can get the area of the triangle, 1/2 of the base, which is 1 over 15. Use Pythagorean theorem to get the value of the height, and we can get the area, and then just plug it right into the equation. The current times the area times magnetic field equals 0.08 newton meters. Torque. We do the same thing with a square. I didn't draw it out because we know a length of a side is just going to be that 0.4 meters over 4, so 1/10 of a meter. the area is just going to be that squared. Use the same equation again, and we'll get 0.104 Newton meters. This is where I left off for part 2, but basically it's the same thing. It's a circle, so we can get we know that this is going to be the 0.4, the length of the wire is the circumference. It's 2 pi r. So we can get the r, then we can do the area, which is pi r squared, and from there it's the same thing. And the circle is the one that has the greatest amount of torque on it. And the rest is in part 2. So that is it.